Okay, so picture this. You're standing by a really powerful river, right? You can feel the water swirling past. Or maybe think about like heat spreading across a room. Can't see it, but it's moving.
Yeah, or even the air flowing over an airplane wing. It's all dynamic. Stuff is happening, changing, flowing.
Exactly. And the question is, how do we go beyond just sort of observing this to actually measuring it? Understanding the mechanics underneath.
Well, that's where the physics comes in, and the math, really. And that's what we're getting into today.
Okay.
The deep dive into vector integral calculus.
Vector integral calculus sounds a bit intense.
It is foundational stuff, yeah. It gives us the precise tools to understand how fields behave. And fields can be anything: temperature, fluid speed, forces.
Yeah.
How they change and flow through space.
Okay, so what's our mission here? What are we trying to achieve with this deep dive?
Well, we're going to unpack 3 really powerful mathematical theorems, and we're using a fantastic source, the Feynman Lectures on Physics, specifically Chapter 3 of Volume 2.
Ah, Feynman. Always good stuff there.
Absolutely. And Feynman saw these theorems as, not just formulas. He argued they're the key, the language, really, for understanding what things like gradient, divergence, and curl mean physically.
So it's like a shortcut to getting the intuition behind the math.
You could say that. He basically said these integral formulas are as vital for field theory as, say, conservation of energy is for understanding particles. They show you the meaning of divergence and curl, which otherwise just look like, well, differential operator.
Right, just symbols on a page. Okay, so let's start with understanding change itself. Gradient and line integrals.
Okay, so gradient. Most people probably have some idea, right? It points in the direction where something changes fastest.
Like on a hill, the gradient points straight up the steepest slope.
Exactly. Or with temperature, the gradient shows you which way to go to get warmer fastest and how fast the temperature is rising in that direction. It's got direction and magnitude.
Okay, got it. Now, how does the line integral fit in?
So, imagine walking along some specific path through that temperature field or any field. A line integral is basically a way to add up contributions along that specific path.
How does that work, like step by step?
Well, you break the path into tiny, tiny little steps. For each tiny step, you look at the field value there, maybe just the part of the field pointing along your step, and you multiply that by the length of your tiny step.
Okay.
Then you sum up all those little products for every tiny step along your whole path. It's like accumulating, say, the total work done by the field on you as you walk that path.
Right, like adding up all the little pushes or pulls.
Precisely. And this leads us straight into the first big idea, the first theorem, sometimes called the fundamental theorem of gradients.
And what's the core insight there?
The really cool thing is, for certain types of fields that are gradients of something else, called scalar potentials, the path you take doesn't actually matter for the total change.
Wait, really? The path doesn't matter at all?
Nope. Only where you start and where you end. So for a scalar field, let's call it CSI, the difference in its value between point 1 and point 2 is just the line integral of its gradient. And you can take any path between point 1 and point 2, you'll always get the same answer. PSI at point 2 minus PSI at point 1.
That's the mountain example again, right? Your total climb, the elevation change, only depends on the start and end altitudes, not which trail you took.
Exactly that. It connects the local change, the gradient everywhere, to the overall total change between 2 points. Super fundamental, especially for things like gravity or electric potential where you have potential energy.
Okay, that makes sense. Linking local steepness to overall height difference. So moving from just change to flow. Let's talk flux and divergence.
Right, flux. The easiest way in is probably thinking about heat flow. Imagine heat flowing through, a block of metal. And you imagine some closed boundary, like a sphere. Inside that metal, how much heat is flowing out through that sphere's surface?
You'd have to measure the heat coming through each little bit of the surface, wouldn't you?
You would. You'd look at the heat flow vector, that's heat per area per time, and for each tiny patch of the surface, you'd figure out how much of that vector is pointing straight out, perpendicular to the surface. Multiply that normal component by the tiny area and add it all up over the whole surface.
Okay, that's the total outward flow.
That's the total heat flux out, and the idea of flux is broader than just heat. It's the surface integral of the normal component of any vector field.
Even if it's not actually flowing like water, like an electric field.
Yeah, exactly. The math works the same. You're basically counting how much of the field pokes through the surface.
Okay. Now, you mentioned something about divisibility.
Yeah, this is neat. If you take your volume, say a big cube, and you imagine cutting it up into lots of tiny little cubes inside, the total flux out of the big cube is just the sum of the fluxes out of all the little cubes.
How does that work? Don't the inside faces matter?
Well, think about two little cubes right next to each other. The flux going out of one cube through their shared face is exactly the flux going into the other cube through that same face. They cancel out perfectly.
Ah, I see. So only the flux through the outermost faces of the big cube remains.
Exactly. All the internal fluxes cancel. This is super important because it lets us think locally. It leads us right to the meaning of divergence.
Which is flux per unit volume.
Pretty much. If you do the math carefully for one of those tiny infinitesimal cubes, calculating the net flux out through all 6 faces, you find something amazing.
What's that?
You find the net flux out of that tiny cube is equal to a specific combination of derivatives of the field components at that point, all multiplied by the tiny volume of the cube.
And that combination of derivatives is?
That's the divergence. Del dot C, or partial Cx dx plus partial city plus partial sissies. So the divergence of the field at a point is literally the outward flux per unit volume right at that spot.
Okay, so if the divergence is positive,
it's a source. Field lines are spreading out from that point, like water from a faucet head, average over a tiny volume.
and if it's negative,
It's a sink. Field lines are converging, like water going down a drain.
that gives it a really clear physical meaning. Source or sink strength.
Exactly. And this leads directly to the second big theorem, Gauss's theorem, or the divergence theorem.
Okay, lay it on me.
Since flux is additive and divergence is flux per volume, you can scale up from the tiny cube. You just add up or integrate the divergence over the entire volume inside your closed surface.
And that sum should equal.
The total flux through the surface. So Gauss's theorem states, the integral of the normal component of a vector field over a closed surface is equal to the integral of the divergence of that field throughout the volume enclosed by the surface.
Wow, okay, so it connects a surface integral, something happening on the boundary, to a volume integral, something happening throughout the inside.
That's the power. It links the boundary to the bulk. Immensely useful. You can trade a surface integral for a volume integral or vice versa, depending on what's easier to calculate or understand.
Can we see how this works in practice, like with that heat diffusion idea?
Sure. Let's go back to heat. If heat is conserved, meaning it isn't being created or destroyed inside our volume, then any decrease in the heat inside must be because it flowed out through the surface.
Makes sense. Heat leaves, so the amount inside goes down.
Right. So the rate of heat loss per unit volume must equal the net heat flux out of that volume surface divided by the volume. Using Gauss's theorem, we can relate that surface flux to the volume integral of the divergence of the heat flow vector. This gives us a differential equation. The rate of change of heat density equals the negative divergence of the heat flow vector.
Okay, rate of change equals minus divergence.
Then we need a physical law. Fourier's law says that heat flows from hot to cold, and the flow rate, the sheet flow vector, is proportional to the negative gradient of the temperature. Steeper temperature drop, faster heat flow.
Right, heat flows downhill, temperature-wise.
Exactly. Now, combine that with the conservation law. And if we assume the heat content is just proportional to temperature, like through specific heat, you substitute Fourier's law into the conservation equation.
And what pops out?
You get the heat diffusion equation. It says the rate of change of temperature over time is proportional to the Laplacian of the temperature. The Laplacian nabla squared basically measures how the temperature curves or differs from the average around it.
And this equation describes just heat.
Oh no, that's the beauty. It describes diffusion in general, gas molecules spreading out, neutrons scattering in a reactor, lots of things. It's a truly fundamental equation that pops up everywhere, all thanks to these underlying principles like Gauss's theorem and conservation laws.
That's pretty amazing. Okay, so we've done change, gradient, and flow out, divergence.
Right.
What about swirliness? You mentioned curl.
Yes, curl. And circulation. Let's start with circulation. Imagine you have a vector field, maybe water currents again. Circulation is what you get if you integrate the field's component along a closed loop path.
So instead of going from A to B, you go all the way around and back to the start.
Exactly. You go around a closed loop, and at each tiny step, you see how much the field is pushing you along the direction of the loop. You add all those contributions up for the entire loop.
What does that tell you?
It measures the tendency of the field to swirl or circulate around that loop. Feynman used the analogy of a tiny paddle wheel. If you stick it in the flow, how much does it want to spin? Circulation captures that rotational tendency around the loop.
Okay, the spin factor. And does this have that same divisibility property as flux?
It does. If you take a large loop and tile the area inside it with lots of tiny little loops, the circulation around the big loop is just the sum of the circulations around all the tiny loops.
And the internal lines cancel again.
You got it.
Wow.
When you go along a shared edge between two tiny loops, you travel one way for the first loop's circulation and the opposite way for the second loop's circulation. Those contributions cancel out perfectly. Only the outer boundary remains.
Neat. It's the same cancellation trick. So this leads to curl.
Yes, curl, which is basically circulation per unit area. Imagine one of those tiny loops, say a tiny square in the sight plane. You calculate the circulation around its four little sides.
Okay.
When you work through the math, approximating the field changes across the square, you find that the circulation around that tiny square is equal to a specific combination of derivatives, partial sig s minus partial sig d, multiplied by the tiny area of the square, dx d.
And that combination is?
That's the z component of the curl. Curl easy. So the component of the curl perpendicular to a tiny surface tells you the circulation per unit area right at that point for a loop lying in that surface. It measures the intensity of the field's swirl at that point.
It's like a point measure of rotation.
Exactly. A measure of the local vorticity or swirliness. And remember the right-hand rule. Curl your right fingers in the direction you go around the loop, and your thumb points in the direction of the positive curl component associated with that circulation.
Got it. Right-hand rule is key. So this must lead to the third big theorem.
You guessed it, Stokes' theorem. Just like with divergence, we can scale up from the tiny loop, we add up or integrate the curl over an entire surface.
How did that work? You're summing up the curl over an area.
Right. Remember, the curl component normal to a tiny area gives you the circulation per unit area. So if you integrate the normal component of the curl over a whole surface, you're essentially summing up the circulations of all the tiny loops that make up that surface.
And because the internal parts cancel.
You're left with just the circulation around the boundary curve that defines the edge of that surface.
So Stokes' theorem says?
The line integral of the tangential component of a vector field around a closed loop, that's the circulation, is equal to the surface integral of the normal component of the curl of that field, taken over any surface that has that loop as its boundary.
Any surface. Does the shape of the surface matter as long as it has the same edge?
Nope. As long as the loop is the boundary, you can use a flat surface, a bulging surface, whatever is convenient. The integral of the curl's normal component will be the same. It's incredibly powerful.
Wow. Okay, so it connects a line integral around a loop to a surface integral over the area inside. That seems really fundamental for anything involving rotation, like magnetism, fluids.
Absolutely crucial for both electromagnetism and fluid dynamics, yes. It links the behavior on a boundary line to the rotational stuff happening across the surface it encloses.
Okay, these three theorems are clearly powerful on their own. How do they, fit together? What are the consequences?
Great question. Let's look at curl-free fields first. If a field's curl is zero everywhere, what does Stokes' theorem tell us?
If the curl is zero, then the integral of the curl over any surface is zero. So the circulation around any closed loop must be zero.
Exactly. And if the circulation around any closed loop is zero, what does that imply about the line integral between 2 points, say A and B?
Well, if you go from A to B along one path and back from B to A along another path, that makes a closed loop. The total integral must be zero. So the integral from A to B must be the negative of the integral from B to A along the other path. Or, wait, it means the integral from A to B is the same no matter which path you take.
Bingo. Path independence, just like we saw with the gradient theorem. And if the line integral is path independent, it means the field must be the gradient of some scalar potential function.
It connects back. So curl-free is equivalent to being a gradient field.
Essentially, yes. If curl F equals 0 everywhere, then F equals grad Cti for some scalar Pi. Think gravity or static electric fields. They're curl-free, and they have potential functions, gravitational potential, electric potential. This connection is super useful.
Okay, that's one major consequence. What else?
Here's another beautiful identity. The divergence of a curl is always 0. For any vector field C, div curl C is 0, always.
Always 0. How does that come about?
You can kind of see it by combining the theorems. Imagine applying Stokes' theorem to a closed surface, like a sphere. A closed surface doesn't really have a boundary loop, or you can think of the loop as having shrunk to a point. So the circulation around the boundary is zero.
Okay, so the surface integral of the curl over a closed surface is 0.
Right. But wait, Gauss's theorem relates the surface integral of a vector over a closed surface to the volume integral of its divergence. So if we apply Gauss's theorem to the vector field, curl C, the surface integral of curl C equals the volume integral of div curl C.
And since the surface integral is 0,
The volume integral of div curl C must be 0 for any volume. The only way that can be true is if div curl C itself is 0 everywhere.
that's elegant. What does div curl C equals 0 mean physically?
It means that any field that is itself a curl of some other field cannot have sources or sinks. It must be divergence-free. Think about magnetic fields, a B field. Maxwell's equations tell us div B equals 0, 0. There are no magnetic monopoles, no sources or sinks for magnetic field lines. They always form closed loops.
And magnetic fields can be expressed as the curl of another field, the vector potential A, B equals curl A.
Exactly. So the mathematical identity div curl A equals 0 perfectly matches the physical reality that div B equals 0. The math reflects the physics.
This really does tie everything together. These theorems aren't just isolated tools.
Not at all. They're deeply linked and form the mathematical language for so much fundamental physics, electromagnetism, fluid flow. These theorems are woven into the fabric of how we describe these phenomena.
Okay, let's try to quickly summarize the big 3 takeaways then.
Sounds good. First, the gradient line integral theorem. The total change in a scalar potential between 2 points is the line integral of its gradient, and it doesn't matter which path you take.
Right, path independence for gradient fields.
Next sec.
Gauss theorem, the divergence theorem. The total flux of a vector field out of a closed surface equals the volume integral of the field's divergence inside. Boundary flow equals internal sources sink summed up.
It connects the surface to the volume. And third, Stokes' theorem. The circulation of a vector field around a closed loop equals the surface integral of the normal component of its curl over any surface bounded by that loop. Boundary loop behavior equals internal swirl, summed up.
Links the loop to the surface inside.
Okay.
And the main point is, these aren't just math exercises.
Absolutely not. They are the language we use to describe how things genuinely flow, change, spread out, and rotate in physical space. They give concrete meaning to the derivatives gradient, divergence, curl by connecting them to integral properties over distances, areas, and volumes. They let us see the physics in the math.
They reveal the inner workings.
Oh.
Okay, makes sense.
So that brings us to maybe a final thought, something for you, the listener, to chew on.
Okay.
We've seen how divergence tells us about sources and sinks, and curl tells us about swirliness. We saw that if curl F, then F is a gradient. We saw that if F curl A, then div F equals 0. But what about a field that is both divergence-free and curl-free? Div F equals 0 and curl F equals 0.
No sources or sinks, and no swirliness. What kind of physical situation would that describe? Where might we encounter fields like that in the universe? What would they represent?
Yeah, what does that imply? Think about it. Maybe think about fundamental fields or conservation laws. It's something to ponder.